Welcome to our final section in chapter 2 for the factorization of A, or A is equal to OU. Actually solving the equation AX is equal to B. We've been doing so much OU factorization. Today, essentially, this section is going to break it down into two videos that are both going to be somewhat shorter because the topics that we're looking at we aren't super in depth where I think you really need a face-to-face instruction, but can look and kind of based off of notes and things like that. So I'm only going to highlight a couple of important features from the text, from the lecture notes, etc. And then, of course, if you are in the online class, then you can always reach out and ask questions from there. So this video specifically, we're going to focus on permutation matrices. So a permutation matrix, which we've seen before, is essentially typically notated with a capital letter P. But one of the defining characteristics of a permutation matrix is that it has a 1 in every row and it has a 1 in every column. So like in this example here, it fits that definition. Every other entry then is 0. And how you can kind of picture a permutation matrix is that it's almost the rows of the identity matrix reordered. And the reordering is very, very important because if you'll notice, this contains row 3 of the identity matrix, this is row 1, and this is row 2. And in the text, and what I would like to do here as well is, if I multiply P times a vector, we'll actually see what type of permutation reordering that this matrix does to a vector. So in particular, if I multiply these two things, 0, 0, 1, 1, 0, just to repeat writing it, times the vector x1, x2, x3, notice that the first row by column will give me x3. So notice third row of the identity matrix gives me the third option up top now. 1, 0, 0 is going to give me x1. And then 0, 1, 0 is going to give me x2 in the third spot. So notice that what this permutation is doing, if this is row 3, this is row 1, and this is row 2, these are corresponding to these entries and where they're going to be now placed in terms of the order. So instead of going x1, x2, x3, notice we're now going x3, x1, x2. And permutation matrices, there are many, many different combinations. Dr. Strong gets into the total number of possible combinations, which I'm not going to dig into too much again with this course being more geared towards high school. I'm not going to go too advanced in terms of topics. But one of the interesting things to see from this, in particular with this permutation matrix, is what happens if we continue to multiply by the same permutation matrix. So if I took this and instead I did p squared times x, and I wanted to do this multiplication again, in other words, what if I wanted to apply the permutation to our answer that we got from doing p times x? Well, if I do that and we're following the same permutation, this is going to take row 3 and make it row 1. This is going to take row 1 and make it row 2. This is going to take row 2 and make it row 3. In other words, it's almost like a conveyor belt where these entries are falling and the next one, the last one, then moves to the top. So like this entry, if I did p squared times x, or p times our result from px, is going to give me x2, x3, and x1. And something that's really, really interesting, that is, if I multiply by another p, so if I do p to the third, aka p times p squared x, it's going to take me back to the original vector, column vector for x. And so by the time I get to p to the third is I. It is the identity matrix. It does not change my column vector x. We get back to the original if I walk through that. So it's this kind of cyclical pattern, which is really interesting when it comes to the multiplications. And he digs into a couple of different examples, whether it's a 3x3 or a 4x4. The last thing I want to talk about, at least in the introduction for a permutation matrix, is something that he points out at the bottom of page 64. And it's this idea of the inverse of a permutation matrix. As you think back to this unit, one of our biggest topics in the last really the whole unit, if you really think about it, starting with section 1, section 2, and then into section 3, Finding the inverse of a matrix is a big topic and relative with the elimination matrices and knowing if A is invertible. Well, because, again, there's this is essentially a permutation of the identity matrix. These matrices are singular, so they're non-singular, so the inverse exists. We can find it. And it turns out that the inverse of a permutation matrix is what's referred to as the transpose. And this is the second big idea in this section that we'll talk about and learn more about in the next video, just kind of breaking it up. And so again, what a transpose does is it takes the original matrix that we have and then it changes rows and columns. So row 1 becomes column 1, row 2 becomes column 2, row 3 becomes column 3. So the transpose would essentially be 0, 0, 1, and then next entry 1, 0, 0, and then 0, 1, 0. So again, you can kind of see that in terms of the way that it's transposed. Still, it's a permutation matrix because it's every column and every row has a 1 in it. And if I do the multiplication row by column, I'll get 1 in the 1, 1 spot, zeros everywhere else because they're not going to line up. Here, 0, but then 1. We get the identity matrix out of this. And so just a really interesting correspondence that P inverse is the transpose. Which again, we'll define this more because obviously you can kind of see the impact and where it, knowing how to transpose a matrix can come into play. So it's kind of a tease that we'll dig into a little bit more later. There are properties that are listed at the top of page 65. Those are pretty straightforward. It's the last one that I want to focus on and really kind of hit on before we end essentially end this video. And it centers around this idea that when we're going through and trying to do factorization A into LU, or if you want to think about it in terms of how we viewed it, that we want to multiply an elimination matrix times my matrix A to change it into upper triangular. There were times, and we hadn't seen it in the previous section at all, but there are times my matrix for A where as we went through and did the elimination, I would get a non-zero pivot in one of the rows. And so the way that we could fix that, so that way I could continue transforming and solve and use back substitution, is to use a matrix P that could then permutate and move a pivot into that non-pivot section that we didn't have. And if you remember, I had to end up pausing and breaking up the last video because I thought we were having one of those situations, but we actually didn't, as we kept performing the elimination matrices. But he gives an example of a matrix where this arises, and this is kind of our first big one. And in the end, what we'll kind of talk about and find out is that it really doesn't matter when we apply this permutation matrix. So why not apply it at the very, very beginning? Let's, as we need to look at the problem, apply that permutation so then there is streamlined, there is no 0 in a pivot spot when we can't have it. And we solve that before we even begin, which is really fantastic. So let's look at a matrix for A, which is going to be 1, 2, just going down the columns 3, and then 2, 4, 7. And then what's really interesting is he leaves the last column as parameters or constants, ABC. And so if we were to perform elimination, we would want to go through and choose, this is my first non-pivot. We want to zero out the 2 entries below. To zero out those entries, we're multiplying the first row by 2 and then subtracting from the second row. So if I do that first elimination for 2, 1, just to keep with the same notation that we had earlier, first row would stay the same, 1, 2A. My second row would be 0, and then 4 minus 2, which is again 0, and then B minus 2A here. My third row, so let's just go ahead and apply now E3, 1 as well. I would multiply the first row by 3 and then do the subtraction with row 3. So 3 minus 3 is 0. 7 minus 6 is 1. And then C minus 3A would finish off my third column in that 3, 3 spot. And so you'll notice that when applying the elimination matrices, we get to this section here where, unlike what we had in the example that I kind of froze on, I have a non-zero pivot here, but I have a zero pivot point, which we cannot have. And one of the ways that we could fix this, as long as this is not zero, so again, we're assuming that this is not zero, because if it is, then this is a row of zeros, the matrix is not invertible, it cannot be factored into L and U. Then what I'm going to do is swap these two rows. We apply a permutation matrix where let's let P keep row 1 the same, but swap row 2 and row 3, so this becomes 0, 0, 1 and 0, 1, 0. So if I multiply by P now, here it's going to swap my rows, and now I'm going to have a non-zero pivot in that 2, 2 spot that I can start working with. So 0, 1, C minus 3A, and then 0, 0, B minus 2A. And because of the swap and the way that the problem is written, a really bad right bracket there. Notice non-zero pivot, and again, we're assuming that B minus 2A is not 0, so there's my last pivot point. And so instead of applying this permutation here at the end, as stated before we looked at this example, the idea is I can actually go ahead and apply this permutation at the very beginning. And if I did that, then this row would already be here in terms of the cancellation, because we would still apply the same multiply by 2 and subtract. We're just now doing it to row 3. And I would get 0, 0, and then my non-zero pivot. So permutation matrices can happen anywhere along the line. And if that's the argument again, if that's the logic, then why not set it up at the very, very beginning? And that's where we get this PA is equal to LU. And so permutation matrices, again, are used in particular to help resolve this issue when I have a 0 along the main diagonal. Can we swap another row? If we can't, then that's telling us something about our problem that we talked about previously. But if I can, then we create this factorization using P. Now, he gives a really interesting way to keep track of your permutations. And this is something that I hadn't really seen before, but it's an interesting take, is to add kind of an extra column labeled 1, 2, 3 to help label the rows. And so as you go through and you solve your problem, you don't really apply any of the algebra to this. You're just tracking where the rows are for the original matrix A. So when I get to this point here where we need to swap two rows, we're literally now swapping these numbers, and so it's telling us what that permutation matrix needs to be and what we can apply at the very, very beginning. So it's just a way to track as you're solving the problem. And I could see that getting a little messy as the matrices get a little bit bigger and as we're walking through and doing that kind of algebra. But I can also see the use of it, in particular, of just trying to figure out what that permutation matrix P is for. If you're somebody that's going to be going into numerical analysis classes, computer programming, using linear algebra in that kind of sense, in particular digging into the actual algorithm that you would apply in computer software, there's something called partial pivoting that I remember learning about, and I always thought was kind of weird because by hand, you typically want this to be, you want your pivot to be a 1, because that's just going to make your multiplication much easier. You don't have to worry about fractions, etc. But if you're working with a computer program, it's actually better to have your pivot be the largest number in that column before you do the elimination. So if I was to originally look at this, what the program and the computer would do is it would look at each entry in this column and say, oh, well, this is the greatest number, so we're going to do a row swap and use that as my non-zero pivot. And then it will actually perform the elimination steps using this as the pivot instead of the 1 and 2. And so he gives a little commentary with that. And I would highly encourage you to look at that if you are somebody that's going to be looking at coding, looking at that numerical analysis and the computations. It's interesting if you're going to go into that field. But again, granted, this teaching this as a high school level kind of linear algebra course, I'm not going to dive too deep into that. I just kind of leave that up to the reader or the online learner in this case. So last thing I want to show you that he mentions, and again, I'm just going to really kind of just touch on it, just to give a little commentary around it, is this, not necessarily other factorization, but notice that we've been essentially multiplying a matrix A on the left-hand side by a permutation matrix P, and how if I do this, P changes the rows. It's a really important aspect to remember. And one that we talked about back in Unit 1 when we've seen how multiplying on the left-hand side affects rows. Well, if I take another permutation matrix, let's call it Q, if I multiply it on the right side of A, this is going to change the columns, specifically the order. Again, permutation really cares about order of things. So if we ever want to affect, again, the columns of a matrix, we can do that by multiplying on the right-hand side by a permutation matrix. And so he asked a question at the end that really focuses on, if we do this, how does this compare to the column space of A? And I'm going to leave that question as just a challenge question there with this, but just to kind of help describe. And he gives a couple of examples. You'll see them in my notes. You'll see it in the textbook of how this does the reordering, and focusing a lot on the number of different matrices that can be created, different permutations that can be made. Because in actuality, if there are 9 entries in particular for a 3x3 that we've been working with primarily, you have 9 factorial combinations, but we have repetition when it comes to rows and columns. And so that list is a little bit more streamlined. So that's it for this video. In the next video, we'll talk about transposing a matrix and what are some of the things to learn and know that come from transposing a matrix. And then that'll actually round us out. There is an extra lesson 2.5 in the textbook that I'm going to not cover as part of this course, but I'm going to leave off here with 2.4.